For centuries, people have dreamt of conquering the inaccessible, the Mont Blanc Massif. Their bold vision eventually transformed this legendary alpine relief into a prized destination. Scaling the highest peaks of Europe, they had to overcome extraordinary technical challenges. In the air and underground, facing extreme conditions, a century of visionaries and builders designed extraordinary infrastructure. How did they manage to tame this mountain?
When it comes to mountain construction, there are lots of rocks to cut, either to excavate or to drill for bridges, viaducts, tunnels.
From the Aiguille du Midi cable car, which crosses 1,500 meters of elevation without support, to reach a rocky peak at almost 4,000 meters.
At the time, it was the longest, most powerful, largest, fastest, and highest in the world.
To the sheer slopes of the Montenvers railway, cut into the cliffside and the gateway to France's largest glacier, which conceals more than 10 kilometers of hydroelectric tunnels.
Here we are under the mer de glace. What we are seeing and hearing is the torrent of the mer de glace.
None of this compares to what came next. In the mid-20th century, civil engineering faced one of its greatest challenges: drilling an 11-kilometer-long tunnel beneath Mont Blanc.
It was the longest road tunnel in the world, passing beneath the highest mountains in Europe.
Now, with climate change threatening this landscape, new challenges must be addressed. The Mont Blanc Massif's exposed construction, dating from the past century, must be rethought to meet the new environmental reality.
Here in 1995, we were under the ice.
This high-altitude world, once intimidating and unapproachable, is now one of the most visited natural sites in the world. It achieved its reputation through brilliant land use planning and monumental construction work, worthy of the grandeur of this landscape and its legendary peaks. The Mont Blanc Massif is an extraordinary alpine formation. Spanning 400 kilometers squared across France, Italy, and Switzerland, it boasts 20 peaks that rise over 4,000 meters. Among them, the most iconic and the highest summit in Western Europe towers over the Chamonix Valley at 4,805 meters, Mont Blanc. This cross-border giant is the emblem of this world of ice and snow, reigning over an extreme environment in which oxygen levels are low, gusts of winds exceed 250 kilometers an hour, and temperatures can plummet to minus 40 degrees Celsius. That's why, in the past, no one dared venture into this cursed massif, petrified by its vast snow-covered walls and terrifying ice peaks.
In the Middle Ages and 17th century, Mont Blanc was a daunting natural barrier that deterred people. Back then, nobody knew that it contained the highest peak in Europe. One can imagine the valley enclosed and isolated by the surrounding mountains.
Yet people were fascinated by these glaciers and terrifying peaks. They dreamed of conquering Mont Blanc. It wasn't until 1786 that two adventurers, Jacques Balmat and Dr. Paccard, embarked on this ascent. Without ropes, ice axes, or crampons, and with a makeshift encampment, they reached the summit after a 14-hour climb.
That really was the birth of exploration and conquest mountaineering, and the start of a great tourism venture in Chamonix and the Alps.
It marked the beginning of tourism and access to the unknown. High mountain terrain became accessible, and everyone could share the dream.
The tourist quest to conquer the roof of Europe had begun. People came seeking the thrills of the peaks and wanting to gaze upon a world of ice. So they decided to build a cable car, one that would break all records and become a direct gateway to high-altitude mountaineering.
A cable car that reached nearly 4,000 meters altitude, unheard of at the time. It was the highest, fastest, largest, and most powerful cable car in the world.
The Aiguille du Midi cable car. Building this giant was an unprecedented technical feat. This spectacular project was carried out over 4 years in the 1950s by sky spiders, who wove cables to conquer the high mountains. 5,420 meters and an elevation gain of 2,739 meters are crossed in just 20 minutes. When the work was completed, the cable car became the emblem of the valley and one of the most visited attractions in the massive.
The Aiguille du Midi has about 500,000 visitors each year. In February, the busiest days see more than 2,500 people daily. The peak season is summer, when we see the biggest crowds, up to 4,500 visitors per day.
The creators of this dream and cable car hope to build a departure point in the center of Chamonix, allowing access to the mythical summit that offers an extraordinary view of the massif from a breathtaking height.
To successfully achieve this unprecedented ascent of over 5 kilometers, they had to make a cable car in 2 parts. The first section, supported by 3 pylons, crossed an elevation of 1,279 meters, connecting Chamonix to the intermediate station, the Plaine de l'Aiguille, which is the heart of the system. The second section had to reach the north face of the Aiguille at 3,842 meters. An additional vertical drop to be overcome, this time facing a dizzying rock wall.
This second section of the cable car was a true technical feat because the placement of pylons or any line structures was not feasible.
They had to show they could hang a cable from the summit to the ground over a span of almost 3 kilometers, which had never been done before without pylons.
They would need to prove that a cable car could be built on that site. In 1949, Alpine guides from Chamonix and Italy transported a 1.8-kilometer-long steel cable weighing over 1 ton and unrolled it from the summit of the Aiguille.
The major feat of the 1950s was to pull a cable down. Guides carried it on their backs, stretching it between the summit of the Aiguille du Midi and the Plaine d'Aiguille. They left it for the winter to check there were no cable breaks or other issues. The test was successful, and they were given the green light to construct the second segment.
With the wager won, building could start in conditions that were to prove extreme. A network of freight elevators and walkways was woven around the pinnacle of the Aiguille at 3,842 meters. At that altitude, the job is 3 to 4 times more demanding due to the lack of oxygen. On the edge of these dizzying cliffs, the workers were like tightrope walkers suspended on wooden planks.
They were both workers and guides, accustomed to high mountain conditions, unafraid of heights, and skilled in moving along snowy ridges or rocky terrain.
Those tightrope walkers hand-drilled over 6,000 cubic meters of rocks under the central peak in order to anchor the future arrival station.
1,000 tons of material were transported each month at a time when helicopters didn't exist, and everything was done by hand. They used tires to maintain fires, to melt snow or warm their hands, as their fingers would stick to the metal in temperatures as low as minus 35 degrees, or storms with winds of 200 kilometers per hour.
Avalanches, falling rocks, crushing or electrocution. In total, 4 people died in these terrible conditions. The earth-moving work was completed on time, and they had to hoist 80 tons of steel to the peak in order to build the arrival station. Meanwhile, hundreds of cubic meters of concrete had to be poured for the foundations of the pylons spread out along the first section.
We're in the first section of the cable car. We started from Chamonix at 1,000 meters altitude, and we are heading to the intermediate station at 2,300 meters, where the machinery for both cable cars is located.
Here we have the traction cable engines, along with the tension counterweights for the 83-ton support cables and the machinery room.
It's okay for me, we can stop. This cable car has 2 cabins, each with around 60 seats. Both cabins are attached to a traction cable like a chairlift, allowing them to shuttle back and forth. But as it's a cable car, there are also two supporting cables on which the carriages run, enabling their ascent like train tracks, guiding the cabins. When one cabin departs from the intermediate station, the cabin from the summit descends and they cross midline.
The movement of the cable car cabins is controlled in the machinery room. Each section has its own mechanism. The electric motor drives a drive pulley through a reducer. This controls the speed and the force needed to pull the cabins. The pulley then moves the traction cable, which is on a closed loop. This traction cable sets in motion the cabins, which rest on a supporting cable.
This is the supporting cable. It has a smooth surface and is responsible for carrying the weight of the cabin and its load. To move along the supporting cable, there are 8 rollers, which distribute the weight and allow the cabin to travel along the cable. Below is the traction cable, a continuous loop running through the machinery, making the system move.
Given the distance to be covered in the first section, a counterweight system is necessary to maintain a constant tension in the supporting cable. They are connected via tension cables to 80-ton concrete blocks that move within a pit beneath the machinery room at the Plan de l'Aiguille.
The principle is that the supporting cable maintains the same tension, regardless of external temperature, the cabin's position, speed, or load. This happens automatically. Here we can see our tension cable moving, meaning that the counterweight is currently rising to maintain constant tension in the supporting cables.
Plan de l'Aiguille is also the starting point for the second section.
Starting at 2,317 meters and ascending to 3,842 meters.
This part is what made it an extraordinary feat for its time, as the mountain's profile did not allow for the installation of pylons to support the 3,000 meters of cable. There's a total elevation change of 1,470 meters that the cable car covers in 7 minutes at an average speed of 10 meters per second, a technical feat.
As you reach the last 100 meters of the ascent by cable car, the cabin rises vertically.
Since the cable can't be too tight, there's a tension of 100 tons. We start out almost horizontally, and by the end, it's a 100% slope, ascending 1 meter for every meter traveled.
It's almost like an elevator system. Nowadays, few cable cars have this profile.
When the cable car was inaugurated in 1955, it became the highest in the world. Construction work lasted a few more years to develop tourist facilities at the summit, which had to be dug directly into the rock. A panoramic terrace, a relay antenna for television, elevators, restaurants. Man had conquered the Aiguille du Midi. Today, 500,000 visitors use this dizzying installation each year, making it one of the most visited attractions in the region. To cope with this influx, 11 months out of 12, sometimes in extreme weather conditions, the cable car undergoes very strict inspections and constant maintenance.
We don't have a problem opening with no visibility. What really disrupts us is the wind. If it's too strong, it can hinder passing the pylons. If it reaches 70 kilometers per hour, it becomes really critical and we can't be certain of opening.
We experience significant ice. The lowest temperatures recorded at the Aiguille have been close to minus 38 or minus 40 degrees.
That's the de-icing from this morning. Today, there was relatively little ice. When we perform de-icing, it's the rollers at both stations that break the ice on the cable.
We experience storm phenomena that sometimes put stress on the cable. Fortunately, it is regularly monitored and checked. However, when we notice progressive wear, we anticipate this change. That's what we did this autumn.
It took 2 months of labor to replace the traction cable of the second section. In total, nearly 10 kilometers of cable were uncoiled from Chamonix to the summit of the Aiguille du Midi.
We are currently in the inspection phase, meaning the cabins have been detached and we're conducting a magnetic inspection, like an X-ray of the cable. We check the replacement and manufacturing protocol to ensure there are no broken wires or signs of friction. There is a regulatory requirement that before the public can board the cable car, this new cable here must undergo magnetic inspection.
In the footsteps of the visionaries of the 1950s, the Mont Blanc company, which now operates this cable car, has continued to develop the facilities at the summit. The Aiguille du Midi pipe, a 33-meter-long gallery anchored in the rock, lets visitors take a complete tour around the peak and admire Mont Blanc from just a few hundred meters. In 2013, they installed Step into the Void, a glass cage located 1,000 meters above the void.
It's a site for excursions and contemplation. We bring this dream to our clients, access to the heart of Mont Blanc Massif. The thrill, the adrenaline of mountaineering, the effects of the cold, and the lack of oxygen at high altitude are the sensations people are seeking.
The construction of this cable car marked a turning point in the conquest of the summits of this massif. Mont Blanc, the roof of Europe, became palpable and accessible, attracting tourists eager to discover one of the most beautiful panoramas in the Alps, once reserved for mountaineers. The Aiguille du Midi also became the starting point for off-piste routes from Vallée Blanche and its 20 kilometers of glacial terrain. This legendary descent leads to the Mer de Glace and the Montenvers site. There, over a century ago, the extraordinary construction of a railway line began.
The Montenvers Railway was the first tourist attraction in Chamonix and the first high-altitude tourist infrastructure in France.
Since 1909, this little train that climbs the slopes of the Mont Blanc Massif has become the symbol of the valley. Today, it carries an average of over 800,000 visitors per year. It connects Chamonix to Montenvers in just 20 minutes, providing access to the largest glacier in France.
The goal was to discover this sea of ice and the surrounding scenery of the Grand Juras and the Dreux and other legendary mountains to offer this experience, so to speak, to these new tourists.
If this little train can climb 1,000 meters of elevation on these dizzying slopes of 22%, it's thanks to a huge technical feat. One of the most perilous railway projects undertaken at the beginning of the last century. This railway would travel from the center of Chamonix to the Montenvers Refuge at 1,913 meters, the most popular tourist site of the start of the century. With avalanches, landslides, corridors to cross, freezing temperatures, and the steep incline, this was a risky construction project.
The first blow of the pickaxe was struck in 1906. Mountain construction obviously entails a lot of excavation and drilling. People weren't afraid of that. They just multiplied the workforce.
It was a huge undertaking. In 1906, 200 workers from Val d'Ota and Haute-Savoie worked for 2 years to create a trench in the mountain, build a tunnel and a covered trench, manually carve stones, and lay 5.1 kilometers of track from the center of Chamonix.
Many of the workers were stonecutters, and lots of them were very young. In the photos, we see kids of 12, 13, or 15, no older.
The first phase involved leveling the old mule driver's path that took tourists to the Mer de Glace. It had to be widened. The forest was cleared, then the rock split to create a zigzag path along the mountainside. The construction materials were extracted on site. The granite was cut and used to build the support walls and bridge piers. The stones were crushed into sand or ballast to support the railroad ties. It was a true battle of the rails. Hundreds of railroad workers worked around the clock for almost 3 years.
It was truly exhausting work, like the efforts required to construct alpine tunnels where you have to blast through the rocks using explosives and dynamite and build hundreds of meters of walls manually, using pickaxes.
With these grueling methods, they constructed several engineering structures along the line. They carved into the rock for over 100 meters to create the Tunnel des Planards. Higher up, the curved Grépin tunnel, spanning 306 meters, was entirely excavated by hand. bridge its avalanche-prone gullies, workers erected the Montenvers viaduct.
It's our gem, so to speak. A viaduct with 11 arches, all built in granite.
An emblem of this railway route. This architectural masterpiece built on the mountainside is an achievement in itself. A 152-meter-long S-shaped viaduct on a 20% slope. Making such a steep incline was a record at the time. This feat could only be achieved using a rack and pinion system, essential for such a steep gradient.
Simply put, we have two rails guided by wheels. Then we have this tooth-racked section that engages with a cog rail. This is what allows us to climb slopes like the one going to Montenvers at 22%, and also to hold the train back on the descent.
With a height difference of more than 90 meters per 1,000, it becomes very tricky to rely on just adhesion. The train would tend to skid, and safety-wise, braking could also be problematic.
After 20 years in operation, the installation of this rack and pinion system did not prevent one of the greatest disasters in the valley, in August 1927. Just a few minutes after leaving Montenvers station.
When a train departs from Montenvers, it starts on level ground, so we're required to pull out of Montenvers station, then make what we call a switchback. This means that when we have enough momentum and start to tip into the slope, we apply the brakes. There's always a brief period of freewheeling. In 1927, the train was initially moving at 10 kilometers per hour, but the maneuver was performed incorrectly and too late, causing the train to accelerate to 60 or 65 kilometers per hour and plunge off the viaduct.
The engine and the first rail car crashed onto the rocks below the structure. The train was crowded that afternoon. In total, there were 22 fatalities and around 50 people injured. Despite this dramatic accident, this feature continued to be a great success. Tourists flocked to ride the little red train. The track was electrified in 1954 and the steam locomotives replaced by electric ones. Travel time was reduced from 55 minutes to just 20 for the 5 kilometers of slope. But this mountainside track requires intensive maintenance during the winter.
Amongst many challenges, there is a specific maintenance requirement for the overhead catenary, which is rapidly covered in frost, and snow must be removed from the tracks.
This is our snowplow. We have a diesel vehicle that pushes and tows the snowplow. The engine on this old locomotive is used solely to operate the snowplow, so that we can open the line every morning and take our customers up. Without this machine, we'd have to close. At the peak, there can be 30, 40, 50 centimeters or more snow in the morning.
To cope with snowfall during the winter season, the Mont Blanc company reinforced the century-old installation with avalanche barriers along more than 600 meters of the track. This helps secure the track by preventing snowslides and allows them to operate the line all year round.
Driving is one thing, but maintenance, snow removal, and overhead line work, these are what enrich our profession. We genuinely love this extraordinary job.
The Montenvers Railway made the Mer de Glace the most easily accessible glacier in the Mont Blanc Massif. When passengers disembark before this exceptional panorama of France's largest glacier, they have no idea that a gigantic network lies hidden beneath the ice, Les Bois Hydroelectric power plant.
Right beneath their feet lie almost 10 kilometers of galleries. And people don't realize that this is where the water from the glacier is harnessed to produce hydroelectricity.
The Alps generate 1/3 of EDF's hydroelectric production in this region. In the Mont Blanc Massif alone, are 90 glaciers covering an area of more than 150 kilometers squared. These true water reservoirs represent a valuable hydroelectric resource for humanity. Snow falls, accumulates, compacts, and densifies over the years, until it becomes impermeable and transforms into a glacier. The Mer de Glace, 7 kilometers in length, a 40-kilometer squared surface area, and 4 billion cubic meters of ice, 2,500 meters in elevation, is a massive hydroelectric resource. And engineers have recognized this. Since 1973, EDF has been collecting the natural meltwater beneath the glacier to produce electricity.
The Mer de Glace torrent provided by the glacier is collected beneath it and channeled towards the turbine through kilometers of tunnels carved into the mountain. This water is projected at 300 kilometers per hour onto a turbine, which generates electricity.
Commissioned in 1958 at the start of the construction of the hydroelectric power station, EDF's exclusive Les Bois cable car is the only means of accessing the glacier's water intake. It transports workers to the entrance of the tunnels carved into the cliffside.
Here we enter into roughly 3 kilometers of pedestrian tunnels that run parallel to the water tunnels. Everything was excavated using dynamite, and there are traces of this work like sticks of dynamite.
In the summer of 1968, for 5 years, workers dug almost 10 kilometers of tunnels of 2 types. Access tunnels to monitor and maintain the installation, and water tunnels to transport the meltwater from the glaciers to the power station.
We used the pedestrian tunnels. Alongside is another tunnel which transports captured water to the power station for turbine use. These doors are watertight. We only pass through them in winter when we know the flows inside are low, allowing us access.
At the end of the first 850-meter-long tunnel are 319 steps to access the subglacial intake. Navigating this environment of tunnels and stairs shapes the design of our interventions. We must prepare well, because if we forget something, we could lose a day or two. The context influences our operations and maintenance. This intake was commissioned in 2011. It's the most recent intake. Here we are beneath the Mer de Glace, with about 70 meters of ice above. The Mer de Glace has a peak just above our intake, so the ice is still quite thick. We can see and hear the Mer de Glace torrent provided by the glacier. It flows into our intake and then into the galleries. After a few kilometers, it is eventually turbined at the power station to generate electricity. The water captured at 1,560 meters beneath the glacier travels through 3 kilometers of galleries before plunging into a 300-meter-long vertical armored shaft at almost 300 kilometers an hour. At the end of its fall, it drives a turbine connected to a generator that produces electricity in the downstream power plant.
The maximum amount we can capture and turbine is 15 cubic meters per second. This would fill an Olympic-sized swimming pool in 3 minutes. This flow rate is a winter low flow. It's cool and there's snow, so the glacier produces little water. In summer, the flow can be up to 30 times greater. We couldn't be here if we'd be underwater.
The power plant produces up to 113 million kilowatts a year, equivalent to the annual consumption of 50,000 people. Amid the deafening roar of the subglacial torrent, we face the immense power of the water delivered by the glacier. The torrent can carry rocks and sediment, posing a real threat to the pipelines and the turbine downstream. To address this risk, a series of grills attempt to filter out rocks at the intake. But the engineers also designed a desander that is 100 meters long and capable of holding the equivalent of 2 Olympic-sized pools. Located between the intake exit and the vertical shaft, it retains any remaining small solid particles present in the glacial water.
Glacial water is loaded with sand, silt, and small pebbles that, when they hit the turbine at nearly 300 kilometers per hour, can cause significant damage. When the turbine was first operated in the 1970s, it had to be replaced for repairs every 2 weeks. The improvements made to this turbine are what make it special. We now replace it only once a year thanks to enhanced coatings and operational practices that anticipate times when the water holds more sediments, thus preserving the equipment.
But the greatest threat to Les Bois power plant is now the impact of climate change. In spring 2009, the original intake that had supplied the power station for 36 years was exposed to the air, whereas it had been situated below 200 meters of ice.
This is the plant's outdoor access platform for the facilities and intakes. We're downstream from the glacier. In 1995, the glacier was level with those trees over there. That was the edge of the glacier, and it used to rise up and fill the entire area we're standing in now. We've seen about 500 meters of glacial retreat over the past 20 to 30 years. In 1995, this whole area was covered with ice.
Over the past 140 years, the glacier has retreated by 2 kilometers and lost 220 meters of thickness, 100 meters in the last 20 years. Scorching summers have significantly accelerated this phenomenon, and the latest statistics are alarming. The glacier is melting at a rate of 10 centimeters per day. In response to the retreat of the mer de glace, EDF engineers have had to create new water intakes at higher altitudes. Since the creation of the power plant in 1973, 3 water intakes have been implemented, the last 2 in a span of 10 years. Engineers had to move 100 meters upstream of the glacier to ensure continued electricity production.
Our predecessors never imagined there'd be this whole series of water intakes. Today, as we witness the glacier's thinning and retreat, we are forced to adapt to these changes.
As well as production loss, a water intake exposed to open air is a risk to the very structure of the power plant. It becomes vulnerable to rockfalls which can obstruct the intake, block the galleries, and potentially destroy the entire facility.
As long as the glacier is in place and positioned above the intake, it acts as a protective shield. It serves as a lid, safeguarding the intake from the environment and from the moraines on the slopes. This mass of sand rocks is held by the glacier's walls. When the glacier retreats, the risk is that these rocks will fall and block our intake. For example, this phenomenon is what we are preparing for. This entire intake and space are filled with rocks and pebbles. So it all travels along with the water.
Anticipating the aspects of climate change is what drives EDF's teams to implement a new operating model for the power plant in the coming years. If they are unable to create new intakes at higher altitudes due to the inevitable retreat of the glacier, the solution would be to use these intakes that are now exposed to the open air while protecting them.
We are rehabilitating the intake and protecting it with embankments, which are accumulations of rocks designed to prevent larger stones from damaging or blocking it. This way, the water can continue to flow into our galleries through this access point and proceed to the turbine to generate electricity.
The subglacial intake then becomes a surface intake. Engineers can reuse all these galleries, which helps preserve this fragile environment.
We always try to be one step ahead, not waiting for the intakes to be uncovered before intervening. The acceleration of glacial retreat forces us to reassess our strategies, to continue producing and maximizing the use of the water sourced from the watershed beneath Mont Blanc.
When these infrastructures were built in the last century, no one was aware of how the climate would change. In the face of this change, many installations must be monitored, transformed, and adapted. But for how long?
The mer de glace is receding as it attempts to escape the people who come to see it. It is melting and retreating. Stairs had to be built, then a first cable car, then a second cable car to take people further and closer to a dying glacier, which we still try to touch as it tries to escape us.
The Mer de Glace's new cable car had to be built 600 meters upstream from the glacier. 2.5 years were required to design this ascent on the cliffside. Preparations are also underway for an international center for the interpretation of glaciers and climate, aiming to raise awareness about global warming phenomena.
We take all environmental elements into consideration. We want to progress and integrate technological advancements associated with environmental changes. Today, creating a device or changing an operational strategy without taking these considerations into account would put us at a disadvantage.
The development of these infrastructures in this previously isolated mountain range has inevitably led to the emergence of mass tourism. To manage the ever-increasing flow of visitors over the decades, access routes had to be built. The conquest of the mountain passes and peaks wouldn't have been possible without these winding roads. The Route Blanche is this vital artery that serves the towns of the Chamonix Valley. Along 20 kilometers at over 1,200 meters of altitude, 53 bridges and viaducts have been built. 16,000 vehicles, including 2,000 heavy trucks, travel this route daily to reach the Aosta Valley in Italy, thanks to one of the largest civil engineering structures built in the heart of the Mont Blanc massif. In the 1960s, at the foot of the Aiguille du Midi, beneath 2,500 meters of rock, engineers achieved a technical feat that revolutionized the region's road network. An 11,600-meter-long tunnel was dug beneath the mountain. The Mont Blanc Tunnel was an extraordinary challenge, a battle against the giant of Europe. When it was inaugurated in 1965, this tunnel broke all records of the time.
It was the longest road structure in the world, passing beneath the highest mountains in Europe.
The statistics are impressive. 1,200 tons of explosives were needed to blast 550,000 cubic meters of rock. 235,000 bolts were used to stabilize the granite. More than 200,000 cubic meters of concrete were poured to line the vault and walls of the tunnel. How did workers manage to complete this colossal project? And how do you secure a crossing of more than 11 kilometers in a two-way single tube in the heart of a mountain range?
At that time, to travel from one valley to another, one had to cross Mont Blanc to go from the Chamonix Valley to the Courmayeur Valley. So for these two communities, it was extraordinary progress.
During the winter, the pass was shut, so we couldn't even meet. With this tunnel, we connected Southern Europe with Northern Europe. Thus, one could travel from France to Italy in 12 minutes.
It's a means of bringing these two countries together, so it is a significant structure for Europe.
It took technological ingenuity and innovation for the French and Italian states to complete this monumental and unprecedented project. The Mont Blanc Tunnel was the culmination of the conquest of this insurmountable alpine barrier, opening a new route for international traffic both in summer and winter. However, they still had to determine the appropriate route beneath kilometers of rocks that were millions of years old. An Italian land surveyor was tasked with finding the best route. On the mountain, in extreme weather conditions, he assessed the path of the future tunnel. This straight line was to run beneath the Aiguille du Midi and connect the Chamonix Valley on the French side to the Aosta Valley on the Italian side.
It was a route between Paris and Rome, passing close to Geneva. There was the configuration of the Alps with valleys on either side. The aim was to minimize the length, so they chose this 12-kilometer route.
Construction began in 1959. Each country aimed to excavate 5,800 meters of tunnel before meeting in the center. To accomplish this colossal task, the workers would use a jumbo, a 75-ton machine mounted on rails and equipped with 16 drill heads. It carried 25 workers who drilled 140 holes at each stage, into which they inserted explosives.
They each started from their own side with similar techniques, those of the time. They drilled into the rock, placed explosives, detonated the mines, then continued in this way through the tunnel.
Simultaneously, 23-ton shovels cleared away the blasted rocks, which were evacuated in 90 wagons pulled by electric locomotives. This painstaking work yielded an average advance of 8 meters per day. While the jumbo allowed for significant progress, the depths of Mont Blanc would reveal unpredictable dangers. As they progressed, the granite in the tunnel crumbled and cracked after the detonation of the explosives. The miners then had to advance with extreme caution through a narrow tunnel that had to be reinforced and secured.
When digging into a mountain, there is a phenomenon of soil mechanics, a shearing or stretching effect on the rock, which reacts when it's excavated. So as they dug, they reinforced the granite using bolting techniques to ensure the rock's stability.
Long threaded rods measuring 1.6 meters were inserted into the rock. Then metal plates were fixed onto them to secure the granite wall. By the end of the project, 235,000 bolts would be installed throughout the tunnel's vault. 2 years after the start of construction work, the excavation had reached 2.5 kilometers. But the further they advanced, the greater the risks.
Above our heads are about 2,500 meters of granite and glaciers. The main risk for the workers was the influx of water and potential landslides as the tunnel was being excavated.
A large part of the rock under which the tunnel runs is covered by the glaciers of the Vallée Blanche and the Mont Blanc Massif. In December 1961, there was a violent cold water surge beneath the glacier. As a result, 1,000 liters of water per second burst through a breach. The tunnel was flooded to a height of 40 centimeters. Excavation work was suspended for 1 month until the water flow decreased to 300 liters per second. Shortly after work resumed in April 1962, there were 3 large avalanches on the Italian side which crashed onto the construction site. 23 men lost their lives during those 44 months of construction work. The last stretch of this underground hell was excavated on August 14, 1962. The final explosion opened the barrier between the 2 construction sites. The Italian and French teams were finally united as the feat was completed. The challenge was met. 11,600 meters were excavated after 4,600,000 hours of work. Almost 1 million cubic meters of rock material was extracted. It would take another 3 years of work to complete the internal structures. The vault of the tunnel was lined with 200,000 cubic meters of concrete. On the floor, concrete caissons were used to both support the roadway and conceal the tunnel's entire ventilation system.
These caissons were prefabricated as the structure progressed, then fixed together so that now, under our feet, we have caissons and fresh air ducts that supply the tunnel.
At each end of the tunnel, complex wind tunnels were excavated at the entrances of the French and Italian platforms.
Each ventilation station has 4 fans that push fresh air into the ducts, located beneath the tunnel's roadway.
These fans blow 600 cubic meters of fresh air through the 4 ducts beneath the roadway. The air is released through air vents placed every 10 meters along the route. 2 other fans are used to extract the stale, contaminated air through a 5th duct located beneath the roadway. This air is drawn out through air vents located in the keystones of the vault every 300 meters. After these final safety adjustments, the Mont Blanc Tunnel was officially inaugurated on July 16, 1965, after 6 years of work. That year, man had conquered the highest peak in Europe, but one suspected that it would become the scene of one of the most dramatic road accidents of the 20th century.
To date, 8 bodies have been formally identified among the 41 victims claimed by the disaster.
On March 24, 1999, a semi-trailer began emitting smoke in the center of the tunnel. The vehicle caught fire and the blaze became uncontrollable. The temperature rose to 1,000 degrees, causing the concrete slabs and the vault walls to explode. Other vehicles were not alerted and continued to enter the tunnel. The fire would claim 39 lives. 53 hours of terror in the heart of the Mont Blanc Tunnel that would forever traumatize the valley. The installations from the 1960s were no longer suited to the traffic levels of the 1990s, which saw more than 2 million vehicles per year. A massive overhaul took place following this tragedy. In total, 3 years were needed to thoroughly renovate the control and monitoring systems, construct new shelters, improve evacuation methods, and enhance smoke extraction systems. The tunnel would become a global benchmark for security measures.
A whole range of modern equipment was installed in the Mont Blanc Tunnel. Complex ventilation management systems were introduced. In the event of an incident or smoke in the tunnel, these systems allow the smoke to be extracted by creating a zero velocity point.
The point zero was created. The air velocity in the tunnel is stopped at that specific location.
With this new process, operators can instantly control the spread of smoke and focus the power of the air extraction fans on the precise area of the incident. This maneuver was made possible by the installation of 38 pairs of ventilation systems and suction openings placed every 100 meters at the keystone of the central arch.
Smoke from the accident area is prevented from moving and spreading elsewhere. We open the suction trap centered on the incident and extract the smoke, etc. We have a suction power that can reach almost 150 cubic meters per second.
The 2 ventilation stations located at each entrance of the tunnel were also reinforced with 4 new auxiliary air extraction fans positioned throughout the smoke extraction duct. This new technology enables optimal extraction of stale air and smoke in the event of a fire.
Control rooms have been installed on each side of the tunnel with agents working 24/7 who have access to all this equipment and can react quickly to an incident. It is probably one of the most monitored structures in the world. There are 160 cameras in the tunnel and 36,000 data points are continuously analyzed by our monitoring systems. So we have significantly advanced safety in the Mont Blanc Tunnel.
These new air extraction devices are complemented by a structural reconfiguration. 37 pressurized shelters of 50 square meters have been excavated around the tunnel every 100 meters and linked to an independent evacuation tunnel beneath the roadway. In total, the renovation work required more than 18,000 cubic meters of excavation. This connection, now essential to an entire region, continues to be improved and developed. For the past 9 weeks, workers have been laboring 24 hours a day to maintain one of the largest structures in Europe.
Here we have replaced a section of the concrete slabs on which vehicles circulate. We are currently assembling it to secure it to the existing slabs. We are planning for the future. Our goal is to extend the tunnel's lifespan, not by 5 or 10 years, but by 100. So the work we are doing is really aimed at ensuring the structure's long-term sustainability.
From its very depths to its highest peaks, man has conquered the Mont Blanc Massif from every angle. This technical conquest has not been without consequences. Ever since the first tourist facilities, the volume of visitors to the massif has been extreme. 5 to 6 million visitors come to admire these landscapes each year, and more than 20,000 people attempt to climb Mont Blanc. Overvisitation combined with climate change threaten this now fragile area. This major tourist site must become a laboratory for effective solutions by employing a respectful, regulated tourism approach, promoting sustainable development, and reconsidering construction methods.
There are things we did at the time that may now be considered excessive in terms of development.
Today, the goal is not to climb higher, but to climb better, to climb more intelligently. The conservation groups with whom we work closely enable us not to confront climate change, but rather to work intelligently on its evolution and how we react to it.
The technical challenge of the early 20th century has now become a challenge of adaptation. Protecting inhabitants, landscapes, and biodiversity can only be achieved through cooperative and careful management of the environment. The Mont Blanc Massif must remain this wild space that attracts visitors from all over the world.